Welcome to the course Digital Transformation and Technological Innovation. The last session we started our second module, that is digital infrastructure. So now let's start and continue from where we left. So next important point that we want to cover is memory types. Right. So earlier we talked about the memory and the bit and byte in the last few minutes of the sessions, and so let's now talk about the memory types, different types of memory that are there in a computer, right. So first one is random access memory, RAM. So RAM, this is designed to temporarily store instructions and data that need change on switching to different software programs, right. So multiple software programs we might be running, we might be multitasking, right. So therefore we need this kind of memory type is important in a computer, where temporarily we store instruction data, and when we switch to something else, the memory can be then used for that particular to store instruction data of that other program, right. So random access memory plays that role, designed to temporarily store instructions and data and for a particular program, and this will need change on switching to a different software program, right. So different programs that we might be running in a computer, right. So they are supported, they are switching, moving from one program to another. That memory support is coming from random access memory or RAM, right. Now characteristic of this is, one is that it is for temporarily storage, so that becomes one characteristics, and the second is volatile. So RAM is volatile, so that means we will lose data on turning off, or if there is any other kind of disruption to the current, right. In one way or another, either we turn off the computer, or some way the current is disrupted, then this whatever we had stored in terms of instruction data to RAM, that will be that will be lost. So that this is referred as volatile, right. So this is a volatile form of memory in a computer, right, and for temporarily. So if you are running a program, so it will support that storing instruction data, you switch to another, so that same memory then will start storing the other program's instruction data. In case the current is disrupted or the computer is turned off, then again it will be clean slate, so you lose the data. So that is meant by volatile. Now moving to the next memory type, that is read only memory, ROM, right. So this is designed to permanently store instructions and data, right. So the previous one, the RAM, was for the temporarily, because it is within the computer system context, and we are working on programs switching from here to one program to another. But in this case of read only memory, ROM, there are situations where we might need to permanently store instructions data, and these instructions should remain the same. The data instructions that are there, that should remain the same, right. Because the same thing might be executed again and again, same thing is needed for execution or for doing certain computing activity again and again. So therefore we need this kind of memory where our instructions data, they are not changed, they permanently remain the same. So read only memory plays that role. So one characteristic is that it provides the permanent kind of storage, and then the second one is that it is non-volatile. That means when the computer or the current is disrupted or the computer is turned off, right, then whatever instruction data that we had on ROM, that will not go away, that will still be there. So next time when we want that to be used, it will be there. So that is why non-volatile. So what kind of programs it would be, ROM would be needed, what kind of support it provides. So needed for firmware program, for example BIOS. What is BIOS? BIOS, basic input output system. So essentially when you switch on the computer, it will check the peripheral devices, other component, what is there and not. So it will look at the whole scanning of all the computer components and other thing, basic input output system. All this will be done by the BIOS. So BIOS is a firmware program, and instructions BIOS or this firmware program are stored in ROM, right, because every time we switch on the machine, switch on the computer, it needs to again do the same check, right. So therefore there is no change in the instructions and the data, that go with this particular firmware program. Obviously, at times we need to update this, so that kind of support is provided in different variants of ROM, right. So that is there. So needed for firmware program, and then another example is startup bootloader program, that is for OS, right. So this startup or bootloader program, we need to load up the operating system. Operating system is technically or more practically the first software program that we load into computer machine, right. So who does that? Another program, that is startup the bootloader program. Instructions for this is again on a permanent storage, which is ROM, right. So it has to be there every time we switch on the computer, the operating system is supposed to be loaded, right. So who does that? Startup program, and therefore it is supposed to be on a permanent kind of a storage and non-volatile, so that can happen. OS we mean operating system, right. So two memory types we talk about, the random access memory, that is within the when operating system is already there and we are working on different application, we want to switch from one to another, then RAM is needed, RAM support is needed, and read only memory ROM support is needed to actually for the BIOS or the bootloader program, so that we are able to bring up the operating system. Now how to boost processing capacity? So earlier we talked about the different factors in terms of the processing speed and the capacity and all those things we talked about. Now we come to the capacity part again here. So multiprocessing is one way to boost processing capacity. Now what we do in multiprocessing, it is about simultaneous execution of multiple instructions for workload sharing, right. So if we just execute instruction one by one, so obviously the speed will be slower, right. But if we somehow able to execute multiple instructions simultaneously, right, then obviously the speed would be much faster, because number of instructions are getting executed at the same time. So we are moving ahead in a speedy manner. So the workload, the instructions that need to be executed or the processing that need to be done, that workload sharing would be much faster if simultaneous execution of multiple instruction is supported. So how that is supported? Via multiprocessing, right. So one of the ways to boost processing capacity is going for multiprocessing architectures. Now we move on to the term that is called multi-core microprocessor, right. So what is multi-core microprocessor? So this combines multiple independent processors into a single computer, right. So processor, microprocessor or processor, we mean the the CPU, that is the main processor that we talked about earlier. So when we say multi-core, that means multiple of those independent processors we are talking about. So multiple processing cores, if they are there, then we can support this multi-processing architectures. So multi-core microprocessor combines multiple independent processors into a single computer. That means that single computer which is having these multiple independent processors, that means which is having a multi-core microprocessor, right, it can facilitate simultaneous execution of multiple instructions, and therefore it will boost the processing capacity. So workload sharing can be done and the processing capacity can be boosted. Now when it comes to multi-core processor, what is there in the market? Let us look at the PC laptop segment. So the current situation or more modern situation is like this. There are these three dominant firms that are there sharing much of the market share in the PC laptop segment: Intel, AMD and Apple, right. So these three are actually catering to the multi-core processor market PC laptop segment. So if we look at the Intel, typically these are the processor Intel Core i9/i7, and if we look at the number of cores, so how many cores are there in multi-core processor nowadays? So you can see from 14, 16, 20 to 24. So earlier versions or earlier multi-core processor that were there, they were having dual core, quad core, those kind of cores, 2 core, 4 cores, like that. But nowadays we have this is like common popular multi-core processor having 14 to 24 cores, in case of Intel. Some hybrid combinations are there when it comes to cores, different kind of cores combined, the total number is given here. Then the second dominant firm is AMD, right. So AMD has AMD Ryzen 9/7. So these kind of multi-core processor options they have, where they have 8, 12, 16 cores. So these kind of options. So AMD also having their own architecture Ryzen and multiple cores, you can see in terms of the options that they are offering. Now similarly Apple has its own M4/Pro/Max, these kind of options available in case of multi-core processor. So here also you can see 10, 12, 14, 16 cores. So you can see if the PC, if we focus on PC laptop segment, most of the products, most of the options that are available in terms of multi-core processor, we are in double digits in terms of number of cores. PC laptop, the main computer for personal users or sometimes professional use that we use, we are already in double digits in terms of number of cores. So therefore already we are doing multi-processing, right. So multiple instructions can be simultaneously executed in nowadays in most of the computers that we buy, the new ones, because they are having cores in double digits. Now when it comes to organizational context, how should organizations select CPUs, right. So a trade-off is needed here, trade-off in terms of processing speed benefits versus energy needs, size and cost. Because if we go for the processing speed, obviously it is going to be costly, the energy requirement will also be there, right. So cost will also go up. So we need to look at energy needs, size, if we go for higher processing, so size, cost, energy need, all this will go up, right. So we need to strike a trade-off, do our trade-off in terms of what kind of processing speed is needed, and therefore balance that with our other spending that will go in terms of energy needs, because you might have to manage the cooling for those processors because of so much of heat that would be generated because of computer being run for that processing, right. Space would be needed, right, and the cost would also be there. So CPUs with faster clock speeds, that means shorter machine cycle times. We talked about this in the previous session. Faster clock speed, shorter machine cycle times, they need more energy to dissipate CPU generated heat. So while CPU is being generated, a lot more energy that would be produced, so that is to be dealt with. So therefore more energy would be needed just to cool down the CPUs, and they are likely to be more bulkier because you go for speedy CPUs, more expensive, right, than the slower options that would be available in the market. So essentially you have to strike a balance between these different factors when it comes to selecting the CPUs for your organizational context. Moving on, what about processing tasks if they involve large amounts of data, right. So more often than not, when we are in the enterprise context or even in the professional context, whether we are using enterprise systems or AI system, we are working with data. Lots of data information is flowing in even in the enterprise system. So many transactions are happening, all of them many of them will eventually come to will be connected to these enterprise systems or maybe AI systems, right. So large amounts of data we are working in, right. So then what happens to the processing tasks when we work with these large amounts of data, right, those contexts. So when it happens, when we are doing modeling, simulation or analytics, right? Because when we are doing all any of these steps, much of this data would be used in that process, and therefore huge processing need would be there. Even if we are just working with the enterprise system and running our queries to to look at few things, those are also computationally intensive tasks. So even then also the processing task, the processing requirement we need to look at. And so when we are working with large amount data, we want to obtain results faster, right. So how do we achieve that? So different ways: linking multiple processors to work together on the same task, right. So we can figure out ways to link multiple processors and they work together on the same task. So earlier when we talked about multiprocessing, we were saying that multiple instructions, simultaneous execution of, let's go back, simultaneous execution of multiple instructions, right. But here we are talking about the same task, right. We are talking about the same task, and within the same task can we create subtasks, can we create a smaller chunks within the same task, and we can link multiple processors to work together, because then these are subtasks, then we will have to again put together the results to get the final thing, right. So some coordination would be needed. So we need to link, so that linking multiple processor to work together, that coordination is needed because we are working on the same task, right. So the task is broken down into smaller code chunks, right. So within the same task, smaller code chunks are created, and if multiple processors, they are coordinated to work on these smaller code chunks, right, and then we put everything together for our final results. So a form of multiprocessing, this is referred to as a form of multiprocessing called parallel processing, right. This is another word for this, right. So now this is one way that we are working with large amounts of data, huge processing needs. So we can do this linking of multiple processors to work on the same, we can do parallel processing. Now there might be situations where we might have to do massively parallel processing. So there are systems called massively parallel processing systems, MPP system, massively parallel processing system, because you are working with big data, right. So all kinds of data is coming in, structured, unstructured, image, video, text, multimodality, right. So that can be case in enterprise systems also and AI systems also. Different examples of information systems, whether the enterprise ones or the AI ones, we have spoken about in the introductory module, right. So massively parallel processing systems will be needed. So this is a form of multiprocessing that speeds up processing, right. So parallel processing we already talked about, so this is massive. So obviously we are talking about speeding up processing. So what happens here, we link hundreds or thousands of processor nodes, right. Now we are not saying processor, now we are not within one single computer context. Now we have when it comes to massively parallel processing, now we are looking at not just independent processor, we are looking at processor nodes. That means they are more than simple processors, it is not within a computer, these are independent processor nodes. So they have more than processing capability to support the node and the processing. So links hundreds of thousands of processor nodes to work together, because you are working on big data or other those large tasks, work together at the same time, that means in parallel, right. So supercomputers, if we look at modern supercomputers, most modern supercomputers are actually MPP systems or clusters. So clusters are like the commodity versions of MPP systems. So most modern supercomputers are MPP systems, massively parallel processing systems, or clusters. The cluster, as I said, being the commodity versions of MPP systems. Now what happens in massively parallel processing systems? So each processor node has its own bus. So as I said, we are not talking about simply independent processor, they are more than that. So we are saying they are processor node and they have their own bus, a copy of the operating system, right, and executes a specific piece of application code. So this part is same, that is a sub chunk is executed, it might have access to the full copy, but only a specific part, it has responsibility of executing only the specific part of the application code, because the whole idea is multiprocessing, rather massive parallel processing, right. So each processor node has its own bus, a copy of the operating system. The bus is needs for to be connected to other hardware components in the MPP system, right, and executes a specific piece of application code. So there is one particular architecture is one tier architecture, which is also referred as pure MPP, where we have shared memory and storage, right. So each processor node would be using the shared memory and storage for its processing needs, right. This is referred as one tier architecture, pure MPP. So therefore the kind of buses and the kind of connections that would be there, they would be very high speed, right. So this shared memory and storage, it would be like local memory and storage, and therefore the pure MPP system, they will have higher capacity because of lack of latency. Well, there is the commodity version, that is cluster, that is 2-tier architecture, right. In this case, apart from the each processor node having access to shared memory and storage, they might have their own memory. So, each processor node might have their own memory and storage at each node, right. So, this is 2-tier architecture in clusters. So, cluster, as I said, are the commodity versions of pure MPP or commoditized version of MPP, right. So, you can see 1-tier architecture and you need 2-tier architecture to arrive at this. So, obviously, the connections, the kind of connections that are there, they are not matching to the level of pure MPP, and therefore, there is some latency that would be there in clusters. So, therefore, the capacity will slightly go down, but still in terms of supercomputer, lots of supercomputers, they are actually clusters, right. So, they still come into that, providing that high levels of processing. Now, let us do a bit of comparison here, MPP system versus cluster computing system, right. So, clusters, they are built using off the shelf components. That means, whatever components you require, whatever hardware components you require to come up with the clusters, they are taken off the shelves and everything is put together, and that is how we arrive at the clusters. So, that is why I said they are referred to as commodity supercomputers. So, most countries and large companies, if they are having supercomputers, more often than not they are going to be clusters, especially in the global south countries or developing countries, right. There you would see supercomputers are actually clusters, right. They are commodity supercomputers. For example, Param series that we have in our country. Then MPP. So, difference. So, these are more likely designed proprietary as a single custom engineer. So, they are designed for higher capacity, much more capacity, slightly, or maybe at least slightly higher capacity than the what clusters could provide. So, designed proprietary, a single custom engineered machine from the ground up, right. So, these most of the top end supercomputers are actually MPP, right. The lines between clusters and MPP is blurring, but pure MPP is still they are the top end supercomputers, and clusters which are the commodity supercomputers just make to the list. So, MPP top end supercomputers, example Cray EX, IBM Blue Gene. So, these are few examples of MPP supercomputers or MPP systems. So, let us move on. Now, there are accelerators. Now, with the advent of GPUs, which are more like an accelerators, further parallelism can be achieved. So, massive parallelism, whether we talk about the MPP or the clusters, both can use accelerators like GPUs to achieve massive parallelism, right. Further parallelism multiprocessing can actually be achieved through this, right. Moving on, we come back to the memory part, right. So, we touched upon the the processing part a lot. Now, we come back to the memory part here. So, that the decision that we wanted to make about what kind of hardware components would be suitable for our organization information systems, to be able to answer to that, we come to the memory back again. CPU processing is done a lot. So, memory not designed to permanently store data, right. So, we already talked about the volatility and capacity constraints that would be there, right. So, volatility we talked about, and because it is a fast expensive kind of storage. So, obviously, this is not designed to store all kind of data in any way, designed as a volatile thing. So, volatility and capacity constraints are there. So, not designed for permanent storage. Then what is there for the permanent storage? Secondary or permanent storage. Some secondary storage is the common term used, and sometimes permanent storage. So, what are the properties? Non-volatile, greater capacity and economical. So, economical is important factor here, that you need to store large amount of data, and therefore, you would need lots of storage, and therefore, it has to be economical, and greater capacity because you want to store lots of storage, and non-volatile. So, you should be able to access it again and again in a more permanent way, right. So, secondary storage is used to store that data, non-volatile, greater capacity and economical. Now, the question is how to select secondary storage media and devices. There are so many options to pick from. Now, there are a number of factors that we can consider. For example, access method, right. So that secondary storage media or device or product, what kind of access mechanism it is following, whether it is suitable for our need or not. So all those factors will come in access method. Capacity, whether we can get enough of it so that we can store our large amount of data. Portability, whether in different scenarios, whether it cater to different scenarios in terms of production environment or uses, right. So all these three factors we need to analyze to understand how to select the secondary storage media and devices. So let us understand what is these access methods. So first one is sequential access, right. So what is sequential access about? This is a retrieval method that requires data to be accessed in its sorted order. So whatever order the data was stored, the same order the access is to be done, right. So obviously in this way we do sequential access for any kind of access to the data, it is going to be a slow process, right. So the main hardware components are magnetic tape or tape cartridge, right. So these are the main hardware products, right, for which actually give sequential access. So represent bits, how the bits are being represented, because essentially we are talking about data that is being stored. So on off states that we talked about in the previous session, right. So represent bits using a small magnetized area, right. So small magnetized area, they are used to represent these bits of on state kind of thing, similar representation, right. Slower access, right. So sequential access, so slower access, less expensive, the technology is less expensive. So therefore this particular hardware is also less expensive, but extreme longevity, right. That means whatever data that you are storing, that can be there for years, right, that can be there for years. So you have less risk of losing out on your data if you are using magnetic tape or tape cartridge. So that is a very important consideration for many firms, organizations, right. Extreme longevity is very important, and therefore magnetic tape and actually the tape cartridges, they are still in the business, right. So used for data backups and archiving, right, because extreme longevity and you can again get back your data. So archiving, they are most suitable, data backups, archiving. So tape cartridges are being used by the cloud vendors and others which needs to store huge amount of data, right. So archiving and backup are common mechanism to store data, right, but they follow the sequential access. So the access is slower, right. So next one is the direct access. So what happens in the direct access? This is a retrieval method that allows for the immediate retrieval. So earlier one was the sequential slower retrieval, now there is immediate retrieval of data without traversing the storage sequence. So we are not dependent on this traversal through the sequence. So without traversing the storage sequence, we can go for immediate retrieval. So therefore this is direct access is slightly faster than the sequential access, right. Now same kind of product, for example magnetic disk, which is based on the same kind of material. So hard disk drive, HDD, which are actually magnetic disk, same material can also provide direct access, can also be designed to provide direct access. So represent bits using a small magnetized area, because the same material is there, magnetic disk. So way of storing data on off states, zeros and ones is same, small magnetized area, but because it is again the same technology, so slower access but faster than the magnetic tape or tape cartridge, but still it will be categorized as slower access, less expensive. So these two characteristics are shared with the magnetic tape and cartridges, and used for mass storage and cloud drives, right. So whenever large amounts of data you want to store, so used for mass storage and cloud drives. So it provide direct access, you do not have to do traversal, slightly faster than the magnetic tape or tape cartridge. So let us stop here and we will continue our discussion on the secondary storage in the next session. Thank you.